You know how long it takes to set up a pool table? Anyway, okay, we've got pool, if you haven't already figured out. Awesome.
So last year we did our project in the pool, so this year we thought we'd do it on pool.
This is probably better at the moment, but
Much better than the
anyway.
Okay, well, so the history of pool is, it's not really set in stone where it came from when it came to the US, but it most likely was brought overseas by the Dutch or the English settlers. And in the 1800s, it was pretty popular. There was like public rooms where tournaments were held. So you can see in some of the pictures, just tons of pool tables. People did it all the time. And as the game developed, there were rule books made, and that's where the difference in billiards and pool came. They're two different games. There's just some different rules.
They're not terribly different. One is
Yeah.
just basically US version, just a couple changes like meters to feet and stuff, you know.
Yeah.
Silly things,
Measurements.
but a little bit of difference.
Some of the major producers is J.M. Brunswick and Bell, but it's now Brunswick Billiards. And some of the properties of the games is that there's 15 balls and one cue ball, and you can only hit like your pattern, solid versus strike, and you can't hit the 8 ball, which is just one.
Yeah. So I think we just broke it down into little small differences a little bit. I don't know, I kind of went over it a little bit, just the small differences, table size, meters, feet, balls. I think our balls are slightly heavier, and the cue ball is a little bit bigger than the rest of the balls. Other than that, though, there's really not too
Yeah.
terrible much.
The billiards table has 4 pockets, while
Instead of
the
the
pool
6.
table has 6. That's a big difference. So for our first problem, this is how we set up our pool table. We put a piece of tape right here and had positive and negative. So we're doing alternating series, kind of setting up a situation.
Because eventually the pool ball has to stop, so therefore it must converge or something.
Yeah.
As long as we're putting it in calculus.
So this is the summation equation that we use. And n occurs each time it goes across the pool table, starting with negative or positive, negative. So,
So we just broke it down. I mean, okay, we're gonna play. It's not super exciting. You're just gonna see it go back and forth. Anyway, I'll explain how that's going. We just kind of calculated out the times and stuff. It wasn't terribly difficult. It was a lot of velocity stuff for that, but then we were able to figure out this.
yeah,
So,
yeah, so it's convergent.
it's pretty well. Now, we had 2 other trials because, you know, you can never have a decent single trial. And so, yeah,
Play all 3 games too.
for the most part, the numbers were relatively close. I mean, there's a lot of human error that can go wrong in this. It was, you know, it was me instead of a machine.
Yeah.
We're watching the videos.
Yeah.
Awesome. Now trial 3.
Yeah, you can see there wasn't much of a difference. All stayed the same.
Okay.
Okay. Some of the history behind the series is Archimedes, was the founder of it. He was a Greek mathematician, physicist, and astronomer, and engineer. He lived in the 2000 BC or 200 BC era, where he designed many different math properties, and he did a couple different inventions such as the Archimedes screw and the heat ray. And you can see it's kind of like a
Grain elevator. If you guys have ever been on a farm, immediately when I saw his inventions, you can think of a grain elevator. It just moves it up. I would believe that that sort of concept is still in use today.
Yeah.
I'm not sure they changed it much.
So our second problem dealt with elastic energy. So this is the formula we use. And one of our cue balls was tossed at the other one. And you can see.
So basically we came upon this concept after I saw a friend of mine show me this just kind of put it into different terms, I guess. All we're basically doing is a Newton, or the pendulum thing, I think it's Newton's pendulum or something, yeah. Yeah, we're basically doing that on a table with balls and friction and stuff. But it's rather interesting because without the friction that the table causes, for the most part, the balls have a completely elastic collision, so they retain all the momentum combined,
Yeah, you can see that the accuracy rate was 38% about.
which is actually about the percent of friction from the felt.
Yeah.
Crazy enough.
From that stuff.
Yeah.
So we did multiple different trials. This one's the same. We just did the accuracy rate again to see.
Because you can still never have a perfect first try.
Yeah.
It still
No.
works.
And we also did other trials with multiple balls to see like the difference, play around with it.
The Newton pendulum. It's immediately what I go to.
Yeah. It's kind of cool. I like the next one the most. We can really notice that. So we use two balls, and you can see that the two different velocities cause two different
Yeah.
balls to move.
And this one looks a lot cooler in person, I'll give it that, because you can't see the balls hitting at separate times.
Yeah.
So, again, pool tables don't really compare very well. So,
Some of the major things that we saw when we were doing this is that not all the energy was transferred from the first ball to the second ball. So we were wondering kind of why. We figured it was friction and some other human errors and stuff, such as one of the balls, or starting ball didn't stop completely or it bounced back. And it also hit like the pool sticks on the sides. And the collision didn't always happen head on head.
perfectly.
Yeah, it would kind of hit sideways, which would lose energy. And we found this, which was the friction from the belt,
That's how we have that.
which kind of explains some of it.
Okay, cool. Now Leibniz was the mathematician who really discovered or founded elastic energy. We know of him already. He helped in calculus a lot. I don't know, he gave us this formula way over there for that elastic energy in physics and stuff. So, I mean, he's been a great help for all of us.
Yeah. He noticed the big, like the correlation between energy and velocity and stuff, and so did other people, so we knew that it was fairly better.
And now we'll just talk about the other things because it'll be interesting. There's a lot of geometry in pool, but I mean, we try not to put too much into it. But for the most part, when you hit a ball onto the cushions, the sides, it comes off at the same angle that it was hit at. So that's some geometry. You can easily curve the ball. You can do a lot of fun things there. So.
Yeah, it has the basic rules of geometry, like if you hit it at a certain point, like at this angle, it'll bounce off at the same angle. A lot of pool players use that. So,
And so, I mean, we just stuck a little bit of history
yeah.
and stuff. So.
So geometry dates back to ancient Egypt when they were creating the pyramids, and then Euclid elements were created in 300 BC, and they're the basic ones that we learned back in the 8th grade. So.
Okay, cool. Well, the 17th century was coordinate geometry, which is, slightly different. It's proofs and all that jazz. And I believe the 19th century, yeah, I think it says up there, was where we kind of get the geometry or whatever that is most common for us, I guess. I mean, I don't personally, I think it's too much geometry if I'm not doing something crazy. Yeah.
We also thought we'd throw in some force, to use force every single time you hit the ball with the cue stick with this ball. But we thought we'd do this, but we realized this isn't really possible for us to do. It's really hard to do those shots, especially since we use a pool table that go to hole. So, but we noticed, or we know that the cushioning on the side would absorb about 50% of the force. So the ball would eventually stop, because this one's extremely impossible, and you'd have to use like times the amount of force for every single time you hit the ball.
Not feasible for us, we're
Yeah,
not
no.
professionals.
We tried, it didn't work.
Oh, and then we just tossed on some history of force. It'll go back a ways, so give me a minute. Newton and Galileo, I think, yeah. They were way back there when they found all of the forces that came up with the idea of thinking that way. Aristotle and Archimedes were the people that they corrected. You've heard all of Newton's rules, you know, object in motion stays in motion, yada, yada, yada. And then other applications, we did this one. I'll take the easy one, for force at least, you can use it with anything. Movement, air, everything, you get it. Elastic collisions are interesting though. You guys know about nuclear fusion and how like the atoms break apart and whatever? That can all be easily shown with elastic collisions because those atoms hit each other with that elasticity, so you can kind of see how things collide. So like particle accelerators or whatnot, when they collide, that's how they kind of look at it. But other things are just kind of baseball, basketball, simple sports stuff.
Alternating series and other applications are in computer systems and video games. Couldn't really find much else. And geometry is used in a lot of housing, carpentry, a lot of hands-on.
Masonry stuff.
3D.
Awesome.
That's it.
Do we have any questions?